Hi. Today I would like to try and explain to you periodic trends, why they occur, and how easy it is to predict them. Now, the periodic trends, there are four of them that you guys are going to need to know. The first one is atomic radius. Now, you may think that hydrogen would be the smallest element, and it is as far as mass is concerned. However, the smallest radius is actually helium. As you go from left to right along a period, let's say from potassium all the way down to krypton, the size of a particular element, the atom, gets smaller. All right. Just like if you go from top to bottom along a column, the size gets bigger. So that's the first trend. The second trend is going to be with ionization energy. Now remember, ionization energy is the amount of energy required to remove an electron from the outermost level or shell of an element. Now, in the bottom left down here with francium and cesium and so forth, it is at its lowest, okay? It is extremely easy to remove an electron from these guys. In the top right, fluorine, helium, neon, and so forth, it has the highest ionization energy. It is the most difficult to remove from here. The next one is electron affinity. This is a measure of how effective an element is at acquiring new electrons. All right? It's a negative number, but basically that's the amount of energy that is released when it acquires a new electron. Releasing energy is beneficial. It increases stability. So the larger the amount of energy being released, the more affinity it has for an electron. Now in the top right here, it has the highest affinity, at least with fluorine, oxygen, and chlorine. Since the noble gases never want to acquire an electron, they don't have an electron affinity. But still, fluorine really loves to get new electrons, so it has the highest. On the opposite side, francium in the bottom left-hand corner, these guys here have the lowest electron affinity. And finally, electronegativity, which we're going to talk a lot more about when we talk about bonding. Electronegativity is basically a measure of when two atoms are sharing an electron, how much does a particular atom want to hog the electrons? All right, how much does it pull it towards them? So down here, francium and them, when they're sharing an electron, they have the lowest possible electronegativity. Whereas up here in the top right, fluorine has the highest electronegativity. Again, it loves to hog electrons. Now, to try and explain or predict, the periodic trends, the easiest way that I have is to pretend that the elements in the top right-hand corner love electrons, whereas those in the bottom left hate electrons. If you could just remember that, you can remember all four of the periodic trends. For example, up here, if you're talking about size, okay, imagine that if an atom loves electrons, right, it's going to want to take its electrons and pull them close and tight where it is. Therefore, when it loves electrons, it holds them nice and close, thus making the radius small. If it hates electrons, then it pushes them out as far away from it as it can. It hates electrons, therefore it's a very big radius. Now, the same thing goes with electron affinity. When it wants to acquire new electrons, like fluorine here, loves electrons. Therefore, it's going to go out of its way to try and gather new electrons, okay? Whereas if it is on the other side, like francium hates electrons, it's not going to try really hard to get a new electron. So its electron affinity is very small. For ionization energy, same thing. If you hate electrons, it's really easy to lose an electron. If another element comes along and says, hey, give me an electron, something like francium says, here, okay, sure, fine, whatever, don't hurt me. Whereas fluorine loves electrons. It really, really wants them. And therefore, if somebody else tries to take it, it says, no, mine, and it holds on to it really tight, okay? So it takes a lot of energy to steal its electrons. And finally, electronegativity. When two atoms are sharing, it makes sense. If you have something like fluorine up here, it loves electrons. So when it's sharing, it's going to want to take those electrons and hog them. It holds them closer to itself than to the other element. Whereas on the other side, something like francium, its electronegativity is extremely low. When it shares, whatever, and it doesn't care if the other element hogs it. It doesn't pull on them very hard. All right, so just remember, top right loves electrons, bottom left hates electrons. Now, to try and explain why the periodic trends occur. In order to understand that, we need to make sure we understand how the periodic table is actually organized, okay? Now remember, we learned before that the columns on the periodic table, where it says up here 1 through 18, if we just look at the main group elements, not these pink guys in the middle, those are the transition elements, we're not going to worry about them right now, okay? They have weird electron configurations, and we're just not going to worry about it. We're going to focus on the main group elements because that's where the trends best are understood, okay? If you look at just the tall columns and you count what tall column it is from the left, so 1, 2, 13 would be 3, 4, 5, 6, 7, 8. That tells you how many valence electrons there are, or how many electrons there are in the outermost energy level, okay? So if you have anything in column that's, say, 14, all of these guys have 4 valence electrons, whereas everything in column 16 has 6, everything in column 2 has 2 valence electrons, okay? And then also the rows or periods, those correspond to how many energy levels there are. Remember, we learned before that an atom was like an onion, okay, or an ogre. It has energy, has layers, all right? And the electrons occupy these layers. And however many layers it has, you can tell by what row it is or what period it is in the periodic table. For example, in row 3, everything in row 3 here, the outermost energy level is the 3rd energy level, okay? In row 4, the outermost energy level is the 4th, all right? Row 6, period 6, it has 6 energy levels, and so forth, okay? Now, to explain what's going on with this, all right, I want to use this little demonstration thing over here in order to help you guys understand it. Now, let's say we are looking at lithium, all right? Lithium has, since it's in row 2 in column 1, it has 2 energy levels, all right? The first one has 2 electrons in it, and the second one has only 1. Now, when it has that 1 electron, it is separated from the previous row because each electron energy level is filled with negative electrons. Because the negative electrons are both negative, they repel each other. So what I have here, imagine that this magnet represents the nucleus, okay? And the nucleus would be the white whiteboard underneath it. This represents the first energy level and the electrons in it. The next energy level, as I go from hydrogen down to lithium, I add an energy level. Now that energy level is repelled by the first energy level, okay? And this energy level blocks this guy and makes it so that the nucleus, which is positive, cannot attract this one as well. Now, as I go down from lithium to sodium, I'm adding yet another energy level, right? I go from 2 energy levels to 3. So each time I go down a group, boom, I add a new energy level. So you can see if the radius is represented by the distance from the nucleus, which is the whiteboard, up to the outermost energy level, which is right here, every time I go down, I'm adding another energy level, and therefore the nucleus, the radius of the atom gets bigger and bigger and bigger. Also, the attraction between the nucleus and these outermost energy levels decreases. Remember, this is positive. The actual nucleus down here is positive, and it is attracting all of these guys because they're all negative. But the attraction between here and here is decreased because of these middle layers. They do something called electron shielding, and they block, right? They block the attraction between the nucleus and here, thus pushing it further and further out. Okay, so that's what happens when you go down a group. Now, let's say we are starting here at sodium. All right, we have 3 energy levels, boom, 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 and we have 1 electron in this energy level. And let's say instead of going down, we're going to go across. Now, magnesium has 2 electrons, right, in its outermost energy level. And to represent that, instead of putting a new electron on the outermost layer, we're going to go and add an electron to the same layer, okay? And then when I put it in, you see what happens. It got scrunched down just a little bit. If I go and continue and say instead of magnesium, I have aluminum, I go and add another one as well, you can see that it's scrunched down even more. Every time you go from left to right on the periodic table, you're adding more electrons to the same energy level, which increases the attraction between that energy level and the nucleus, thus scrunching it down closer and closer and closer. If I had more of these magnets, I would add all 8 of them, and you'd see it be scrunched down nice and close, which is why argon, even though it has a lot more electrons, is much smaller radius than sodium, because all of these electrons got added to the same energy level, which causes it to scrunch down, and it decreases or nullifies the electron shielding of middle electron layers. So hopefully you can see how as you go from left to right, the attraction becomes greater between the outermost energy level and the nucleus. Whereas if you go from top to bottom, every time you add another electron, every time you add another, let's try this one more time. Every time you add another electron, it increases the electron shielding, causing it to go higher and higher. Hopefully you found this useful. Thank you.